guys, 13th February. Let's start on problem 4. I've actually spent some days doing other stuff, but also when I read question 2, it occurred to me that with theta super A occurring here, maybe we should need some knowledge about the Fourier transform of the character. So I looked a little into it. I don't know if we shall need it, and I don't have any results, but I learned some interesting stuff that might be true. But we'll see what happens. First, this guy, I think we should start on the left-hand side. And then let's just apply the definition here. And that's A divided by N squared. And we should be able to rewrite this to something like this. Or rather, we may change t. So let's take n squared out, take it outside the parenthesis. That should be a t. Were you able to see that? So this guy runs through all of the integers, and then the interior here has the same value. Chi of that has the same value as chi of A. And then instead of summing from, this way we get all the integers, and I just called that A. That's really not right. Let's call it B. B squared, and that's exactly equal to I have to be precise with my n's. So here n went from 1 to infinity. So we go here from 1 to infinity. And then this sum is exactly theta A, 1/2 theta A. a sub of t divided by n squared. So what were we supposed to compute? And that's exactly 1/2 theta of t. Well, there's a factor 2 wrong here. Now, which n's do we sum over here? That's from 1 to n. We were on the right hand side. So therefore we only get the positive b's and naught, of course. Well, never mind the naught. And this guy, oh, there's no half here because summing from 1 to infinity gives theta chi. So we should not have the half there. But then here we are only summing from, and theta a, oh, that's also only from, no, where do we have it? I've just been wondering on which side am I starting? Yeah, I'm starting on the right hand side, and then we should get twice theta. Well, I don't see that. Well, let's start on part 2. So which side should we start on? The left hand side or the right hand side? Let's try the left hand side. And then theta super, which I should have written. And here a is a divided by n. So it should be a divided by n here. And pi a divided by n. Squared pi t, and t, that's t. But this should be squared. Damn it, I should have prepared this. I'll just make a break while I check it. I wrote the formula here, and there we can see that A must be A divided by n, and then it's Tn squared. And now you can see why I thought about the Fourier transform, because if we sum over A, this really looks like the Fourier transform of chi. Well, indeed it does. So I think I would like to have a nice result of the Fourier transform of chi. So I believe I do need what I was working on, and I didn't prove it, but from what we have to prove here, I can guess the relation. We have to prove that the Fourier transform is the conjugate times the g of chi. And I didn't find that formula because I only worked with real characters. What I'll do is that I'll try to write up the equation I believe I have, or I need to prove, and then I'll look at that. That's my claim. I tried to prove it, by the way, but not in exactly this formulation, but I was not able to do it. The conclusion is that I need a break while I work on this to see if I can get any idea how to get along with it. I'm back after lunch, and I'll start by showing you the work I did during the weekend. First, I took the primitive character modular 12, and I have its values here. We've been through that before, and the g of chi is 2 square root 3. And then I program the map giving the Fourier transform, where we use the conjugate of psi. And yeah, I already knew that the Fourier transform of chi taken of 1 gave exactly g of chi. I just wanted to see that happen in reality. And then we compute the Fourier transform divided by the value at unity, and it's identical to the values of chi itself. This is when I had finished doing it. Then I did the same with non-primitive character. This is modulo 4, if we take it, it's still modulo 12 of course, but if we work modulo 4, then it's trivial because the next guy is 9 and then 13. So it's trivial on 1 plus the ideal generated by 4. So it's not a primitive character. And when we compute the Fourier transform and divide it by g of chi, then it's not even a character modulo 12. I tried with 3 and 4 and 5. And 5 was interesting because the no, it's actually because then we have a character with complex values, and wasn't I able to reproduce it? I couldn't get able to reduce this with n equal to 5, so I had to do it, or I solved it by doing it numerically. So the first is unity, the next one is minus I, using the same formula as I had found, and it actually should give plus I. So that means that I was really trying the wrong formula. On the other hand, that was I didn't try to prove it really. I looked at what I had to prove, but I had no idea what to do. So let's see if I can prove this assertion. And as you can already see, I've taken the formula we proved in problem 9 because I believe that actually solves the problem. So we start with the Fourier transform evaluated at A. That was the definition. And this is psi of AB, where psi is x maps to psi in minus extra, or enter. So we use this because we assume that chi is primitive. So that gives chi bar of A chi of B psi to minus B. And this was where I got stuck. I had seen this, but I really couldn't figure out how to change sign on B. And actually it's not very difficult, I think. We just multiply by chi of minus 1, and it's real. So it's equal to chi bar of A, chi of minus 1, g of chi. And that was pretty close to my idea here, except for anything. Well, let's look at it. If we sum this over A, that means that this was wrong. We have to multiply it by, oops, chi of minus 1. Now this green part I see. Instead of using what I have done here, which is very nice, of course, but it's not really relevant. We can use problem 9 directly. So let's just cancel this claim. And work on this. So it's chi bar of A. No, we are summing over A. So it's chi bar of N times G of chi. My God, was that really all? That's really all. So G of chi times theta of chi bar, point G. I'm sorry, that was very easy. I should have seen that. Now, for the next, I believe we must have t in the denominator here. And that means that we shall use the transformation formula for theta A super. I'd rather do this on a blank page, so I have to copy this over to be able to see it. So let's have a little break. I made a new page with the problem 4, and then I took the formula from problem 3 that I think we shall need. So we start with theta chi t, and by part 1, right, and then we can apply this formula directly. And then we need to combine with this. So 1/2 the sum from 1 to n of chi. Yes, that's what we've got. So that gives g of chi. And then theta of missed it here. It's nope. It's theta of chi bar, point, comma, And then this value, and where did 1 divided by square root t go? There's no mention of that, so we need to put it somewhere. Oops, no. Oh yes, it must be square root of course. It must be n squared t raised to minus 1/2. And that's what we should show, square root of n squared t. G of chi, yeah, that was 0.3. The Mellon transform converges for any s with no need for any correction term. So we should just be able to write like this. This is my special infinity sign. There we go, somewhat better. So it seems clear that it falls off exponentially. So how does it behave close to naught? It should fall off exponentially as well. Can that really be true? This is the formula I'm thinking about. When 1 divided by t tends to naught, then theta will go as fall off exponentially, according to 1 divided by t times the square root of t. So it'll still fall off to naught. All right, so that's it. So I actually thought it should work for all s. Oh, that's what it says. It converges for any s. And now we have to compute it. So the problem is which of the formulas we should use, summing over all, or just for positive n. Actually, I think I don't know what I think. Basically, my instinct was to use this formula, but we can just as well use this one, I think. Let's try that, see what happens. This is the problem with these exercises, that there are so many possible ways to go. So I have several ideas what to do, whereas in other problems, just getting one idea is the problem. So let's sum over all m. I believe that doesn't work at all, does it? Well, let's write it up. And yeah, we can just put the integral sign here. And now what was that? That's the one we've had so often. Let's see if I can remember it. And I'll just look it up. Right. And that converges when the real part, oh no, when it tends to naught, then we want this to be larger than, so I think it's just the real part of s larger than 1. I see now, when they say larger than 1/2, it's probably, no, I thought we should use s halves here. Oh, it says 2s, so let's just work as it is. Oh. So pi n squared to minus s and then gamma s and then the sum. Summing over all n. Now, how was, oh, I forgot the chi of n. Chi of n, so we should have used s halves Don't like it. There's something amiss here. To get L of chi s, of course I should have used S halves, but then I'll get something. No, it's still N2S, all right. So this sum actually gives L of chi. So I have 1/2 pi to minus s gamma s L of chi 0.2s. So how close am I? Pi to minus s L gamma s. Wow, it's just a factor 2 off. That was just in the like in the first guy here, where I got an error by a factor 2. That will of course be corrected already second time through. E we got right. I'll make a break and then prepare writing up what we proved before in problem 3E, and then I'll see what I can do, and I'll try to find this error of a factor half actually also on the other page before starting again. Let's first look at the first equation. Here we sum for all n, and then suddenly I change it to only sum for the positive n's. So that means we must have a factor 2 here, which will live all the way until here. So that was that one. Yeah. And oopsie. And the next one, I think I did, this was down in B. Here we sum over all n, theta over all n, but then down here I only use it for the positive n's. So if we say we sum only for the positive ones, then I just have to erase 1/2, and then saying we sum from n going from 1 to infinity. There we go. Right. Let's get it on and make the usual change of variable. This integral equals the integral from 0 to infinity. Just introduce u is the reciprocal of t. And we must now use the transformation formula. So we replace in this formula, we replace t with n squared t. No, of course we replace t with n with t divided by n square, capital N square. Let's see if I can write what it gives. That would make it easier. Oh, we get a g of chi, and then 1 divided by square root t, that's t of a half minus s, times theta of chi t, oopsie, yeah, t divided by n square. And we use the sum over, reduce the definition, and exchange sum and integral. Did I do this right? We will see. So it's d of chi, the sum, and then the integral. That's the usual thing. Pi to minus 1 minus 2s divided by 2, and then n what? Yeah, 1 minus 2s, of course. And the constant is the same. I feel I missed a chi bar here. Pi to minus s gamma x lambda chi 0.2s equals g of chi pi to minus this guy, L of etc. Let's see what it says here. I'm missing a factor n to the s. Thought there was a factor capital N somewhere. It's here. How could I miss that? I didn't miss it. I said it vanished. Never mind. You find that mistake. And I will too when I've turned on the recording.